Okay, so this is going to be over water potential. So when I referred to we can measure the tonicity in a numerical value, that would be water potential. And so water potential is composed of solute potential and pressure potential. Now this symbol is called psi, and it's just like the little thing in how we label our variables for water potential. So pressure potential, to me it looks like a trident. So pressure potential, for our cases, unless it says different, it's going to be 0, and that's for like in an open container. There's no pressure, there's nothing above our container, so it's normal, so it's going to be 0. But like if you had a plunger or something and you change the pressure, then that would change. So usually it's going to be 0 because we have an open container. So then to get water potential, all we need is the solute potential. And solute potential is from this equation negative ICRT. I say negative I cart. Okay, and so there's a couple things that we need to know about this. I is ionization, or I don't know, I think it stands for ionization. C is concentration. R is kind of like, and Q equals MC delta T is like the C, and so that's going to be 0.0831, and it's measured in bars, liters, moles, times Kelvin. And then temperature is the temperature, but in Kelvin. So basically, degrees Celsius plus 273. That's how we're going to find it. Okay, so I'm going to make up a little practice problem. One thing to note about the I, for a thing like sucrose, it doesn't break apart, so that's going to be 1. But for salt, when in water, because it ionizes and breaks into 2, that's going to be 2. So we're going to do, salt, NaCl, 0.5 molar at 23 degrees Celsius. Okay, so now I plug that in. Solute potential equals negative 2, because it's going to split apart, 0.5 molar. And remember, molar is moles per liter of something, or 0.0831 R, and then bars, liters, moles, Kelvin, and then 23 plus 273 is 296 times 296. So when I do these on my calculator, I always start with the temperature, so 296 times 2 times 0.5 times 0.0831, and then times negative 1. So my solute potential equals negative 24.6. And so what this is used for, if you had a solute potential of regular DI water is going to be 0. And so the solute potential of this, or the water potential of this, will be negative 24.6 if it's in an unopened container. And water is going to flow, from high concentration to low concentration. So high being 0 to low, because on a number line, 0's up here, 1's up here, negative 24.6 from high to low, like on the slide. Okay, I hope that was helpful.